Pluto was once regarded as a legitimate planet in the solar system. It is still a dwarf planet that captivates and eludes explanation, located far away from Earth. Despite its previous classification, the most recent bold assertions made by well-known astrophysicists Michio Kaku and Neil deGrasse Tyson have sparked brand new interest in Pluto. They suggested that this ice-covered planet could be heading in the direction of a devastating encounter with Neptune, triggering a flurry of inquiries regarding the plausibility and consequences of such a situation. Could this be an exaggerated theory, or is there proper cause for concern? Let's investigate the potential consequences of an initial collision between Pluto and Neptune. Pluto was originally classified as a planet. However, it was later reclassified as a dwarf planet due to its erratic orbit. This choice has maintained Pluto as a topic of ongoing discussion in the world of astronomy. The most recent leading scientific studies suggest that Pluto's orbital course poses a danger, as it coincides with Neptune's, raising concerns about the possibility of a fatal impact. Because of their proximity in respective orbits, a collision is theoretically possible. Could a collision between Neptune and Pluto actually occur? And if so, what would the implications be for Pluto's orbit? There is no planet in our solar system quite like Pluto. It has its own unique orbit that spans a complex 248 years, indicating that since its discovery in 1930, Pluto hasn't even completed one full orbit yet. However, the peculiarity of Pluto's orbit doesn't end there. It follows a highly elliptical path, deviating substantially from the near-circular orbits of most other planets. Adding to the complexity, Pluto's orbit is tilted 17 degrees toward the ecliptic, making its inclination much steeper than that of other planetary routes. An especially fascinating aspect of Pluto's orbit is its relationship to Neptune's. For approximately 20 years of Pluto's long orbit, it gets closer to the Sun than Neptune, an odd phenomenon that raises the crucial question: why have Pluto and Neptune not yet collided? The answer lies in the powerful forces of gravity exerted by other bodies in the solar system. Following Pluto's discovery, astronomers quickly acknowledged the peculiarity of its orbit. In contrast to the almost flat orbits of the other planets, Pluto's steep angle and elliptical trajectory stood out. The complexity of its path became even more evident as researchers realized that Neptune's orbit actually crosses that of Pluto. Despite these out-of-the-ordinary features, Pluto's orbit has remained remarkably stable, thanks to the gravitational effects of other celestial bodies. The problem of three bodies in celestial mechanics seeks to explain the interactions of planets like Pluto and Neptune, as well as the Sun. Pluto's path can be erratic, and even the smallest changes in its initial conditions can have drastic long-term effects. However, simulations have demonstrated that Pluto's orbit has remained stable over long time scales, indicating that its path, despite appearing chaotic, is not. The significant gravitational pull from Jupiter and other massive bodies plays a crucial role in keeping Pluto in orbit for billions of years. These forces are necessary for preserving the overall order of our solar system and preventing unrest, while Pluto demonstrates a fascinating equilibrium between order and chaos. It's important to acknowledge the inherent difficulties in predicting celestial motion, particularly with irregular orbits. Despite the power of numerical simulations, space remains unpredictable. Events that shape the future are uncertain. The issue raised by astronomers like Kaku and Tyson about a possible collision between Neptune and Pluto may seem remote. However, their warnings have captured the public's attention. If such a collision were to happen, the results could be detrimental to our solar system. The impact would release a great deal of energy, likely destroying Pluto due to its diminutive size and icy composition. The resulting debris could endanger nearby planets and their moons, including Earth. The effects would extend beyond Pluto alone. For Neptune, such a collision could significantly alter its orbit and atmosphere. According to Michio Kaku, a renowned theoretical physicist, understanding Pluto's orbit could offer valuable insights into the physics governing space exploration. Through Pluto's orbit, we can study gravitational interactions and gain crucial information for future missions. Science could benefit from this knowledge, by preparing for potential space threats and enabling exploration of distant regions in the solar system and beyond. Pluto's orbit also has broader implications for research into other trans-Neptunian objects and dwarf planets. Its complexity challenges our understanding of planetary motion, reminding us how unpredictable and dynamic space truly is. The relationship between string theory and the mechanics of the universe emphasizes the importance of understanding the gravitational interactions between planets and celestial bodies. In the event of a collision between Neptune and Pluto, we would witness a defining cosmological event, providing a rare chance to investigate string theories under extreme conditions. The energy released could offer a glimpse into the behavior of fundamental particles and forces at high energy levels, which are central to string theory. Despite the low likelihood of a direct impact on Earth due to our distance from the outer solar system, the scientific implications would be profound. A collision of this nature would offer new opportunities to explore the fundamental nature of the universe, especially in fields like string theory and astrophysics. Pluto's unusual orbit continues to captivate both space enthusiasts and astronomers. The ongoing debate regarding its planetary status has reignited interest in its role within the solar system. The concerns raised by Tyson and Kaku highlight the many forces that govern celestial motion, underscoring the importance of understanding gravity and orbital mechanics. These forces are essential, not only for grasping the dynamics of our solar system, but also for contributing to the broader discussion on Pluto's classification. Its steep and elliptical orbit defies conventional theories of planetary motion. Unlike the nearly circular orbits of nearby planets, Pluto's path intersects Neptune's at specific points during its extended journey around the Sun. Gravitational influences from Neptune and other planets have helped maintain Pluto's relatively stable orbit over the centuries. Yet, predicting the future behavior of celestial bodies remains a complex and uncertain task. The theoretical collision between Pluto and Neptune serves as a reminder of the inherent unpredictability of planetary dynamics. While such an event seems extremely unlikely in the near future, gravitational interactions between the two planets illustrate the delicate equilibrium within our solar system. Research into Pluto continues to provide valuable insights for future space exploration, aiding scientists in studying other distant celestial bodies and deepening our understanding of planetary evolution. NASA's New Horizons mission, launched in 2006, captured groundbreaking images and data about Pluto and its moons during a historic flyby in 2015. This mission revealed fascinating details about Pluto's vast surface, composed largely of frozen nitrogen and water ice. Planes that help us learn more about the processes that shape this distant world. The New Horizons mission's success emphasized the technological advancements and coordinated efforts required to visit the farthest reaches of our solar system. Research on Pluto and its moons gave scientists invaluable insights into the variety of conditions and celestial bodies found in the solar system's outermost regions. These findings have significant ramifications for upcoming missions aimed at investigating additional distant dwarf planets and trans-Neptunian objects. Scientists can use this additional information to further understand planetary creation and the development of Pluto. Pluto's transformation into a dwarf planet has sparked significant discussions regarding how we define celestial bodies within our solar system. This reflects larger concerns about scientific classification and the nature of change in our astronomical knowledge. Understanding Pluto's orbit is essential. It offers insights into the mechanics of space and planetary dynamics, particularly as we venture further out into the wilderness of the solar system. Through Pluto's investigation and its interactions with Neptune and other celestial objects, we keep expanding our understanding of planetary system formation and development. Pluto's discoveries and ongoing research have substantially contributed to our comprehension of planetary motion and the development of a region known as the Kuiper Belt, beyond Neptune, where tiny icy bodies reside. Gaining a handle on Pluto's orbit provides useful information about the gravitational interactions that may have shaped the early solar system, offering essential data for future space missions focused on areas outside potentially habitable worlds. Despite the extremely low possibility of a Pluto-Neptune collision, the study of these distant objects serves as a reminder of the universe's ever-changing nature. As we continue exploring beyond our solar system's borders, the study of planetary orbits and celestial mechanics remains crucial. Pluto's unique orbit provides instructive examples about the planet's complexities and the forces that shape celestial motion throughout history. Ongoing investigation of Pluto's orbit and encounters with Neptune remind us of the universe's erratic and dynamic behavior. With every new finding and theoretical model, we enhance our comprehension of the cosmos and gain further insights into the mysteries of distant worlds. Studying Pluto's orbit not only provides answers about this remote planet, but also aids in forecasting future changes in celestial behavior, helping us better understand the mechanisms governing both our solar system and what lies beyond. The possibility, however unlikely, of a Pluto-Neptune collision underscores the universe's dynamic nature. Research into Pluto's orbit and Neptune's gravitational influence provides vital insights into celestial mechanics. In the meantime, as we investigate these far-off objects, we refine our planetary models and improve our capacity to forecast future cosmic events. There seems to be no end to the field's potential discoveries. Additionally, as technology advances, so will our ability to comprehend and explore the vast and ever-evolving universe. The investigation of Pluto's orbital position within our solar system will continue to enrich our knowledge of the universe for many years. Pluto's orbital behavior and its distinctive interactions with Neptune have long fascinated the scientific community. Despite being designated a dwarf planet, Pluto continues to challenge our understanding of planetary dynamics. The fact that Pluto's orbit crosses Neptune's path, yet avoids collision, demonstrates the complex nature of gravitational mechanics within our solar system. One of the most intriguing features of Pluto's orbit is its resonance with Neptune. For every 3 orbits Pluto completes around the Sun, Neptune completes 2. This synchronized relationship ensures that the 2 planets never get too close, even though their paths intersect. Pluto and Neptune are, in this sense, engaged in a cosmic dance. Their orbits are locked in such a way that they never meet, which makes them unique. This gravitational relationship is an excellent example of the precision and balance in celestial mechanics. The gravitational forces exerted by both Pluto and Neptune work together to maintain orbital stability. Without this resonance, a disruption in Pluto's orbit could have occurred, possibly resulting in a collision or significant changes to its trajectory. Astronomers rely heavily on this interaction to understand how celestial bodies can maintain equilibrium, even when their paths appear chaotic at first glance. The Kuiper Belt, beyond Neptune, is a treasure trove of dwarf planets and icy bodies, with Pluto being the largest known object. The belt's orbital structure provides crucial information about the conditions prevailing in this remote region of the solar system. Kuiper Belt objects, KBOs, and other trans-Neptunian objects, TNOs, are remnants of the early solar system. Studying them allows scientists to peer into the conditions that prevailed during planetary formation billions of years ago. Space agencies, including NASA, are now directing missions to investigate these distant regions. NASA's New Horizons mission, which conducted a flyby of Pluto in 2015, provided us with previously unseen images and information about Pluto's surface and atmosphere. The mission revealed towering plains of frozen nitrogen, mountains of ice, and a variety of weather systems, suggesting that Pluto is a world with active geology. It also highlighted the diversity of Pluto's moons, offering insights into how satellites may develop in the outer solar system. The New Horizons mission exemplified the growing capabilities of modern space exploration. Missions like these not only broaden our understanding of distant Pluto-like celestial bodies, but also pave the way for more ambitious research into the Kuiper Belt and beyond. This mission's success has rekindled interest in exploring faraway regions, potentially inspiring future missions to other objects within the belt. Although Pluto's orbit appears stable, its tilted and eccentric trajectory raises questions about the long-term dynamics of the solar system. Unlike the nearly circular orbits of the 8 major planets, Pluto's inclined and elliptical orbit offers clues about the more chaotic elements of solar system evolution. This behavior suggests that planetary systems, especially those at their outer edges, can change in unpredictable and previously unimagined ways. If Pluto's orbit were to undergo significant disruption, it could have repercussions throughout the solar system, potentially affecting other planetary or Kuiper belt orbits. Some scientists hypothesize that Pluto's interactions with other gravitational bodies, such as Neptune, may offer critical insights into the early evolution of the solar system. As researchers continue to study Pluto's orbit, they hope to uncover more about the forces that shaped our cosmic neighborhood and the role of gravity in determining the paths of planets, moons, and minor celestial bodies.